believe in yourself, for that's the place to start. And I say, hey, hey, what a wonderful kind of day, if we can learn to work.
Hey fans, I'm Ramin, you're the fan. Or you're the fan and I'm Ramin. Doesn't matter, right? Okay, so we're going to cover some stuff before we get into the content of today's video, which is why is light constant, right? That is the main thing we want to emphasize today is why is light constant, right? We won't actually resolve the quantum entanglement speed of light paradox because I need to work on my animations a little bit for that. And so that is just what we're going to talk about right before we get into the video today, right? And so essentially what we need to talk about is my lecture style, right? I enjoy talking, believe it or not, right? But I do and also know that people don't always enjoy lectures. People find school boring because lectures can be boring. I enjoy them, right? I'm built different, so I enjoy the style, but I get it if you don't, and I know most people don't. Thus, the need for animation is born so I can try to grow an audience for these videos, and those who do enjoy the lecture style, lucky for you, I will be starting a math sub-series. So you will get the lecture style in the math sub-series, and that's just probably what's going to happen moving forward with this channel. So with that administration tasks out of the way, let's get back to the paradox we were enamored with, right? If we recall our last episode, we had particle emissions from the same system can be what is called entangled, right? And they are entangled within the same measurement. That is, if I measure something to be on one axis, I will know the information on the same axis of the corresponding particle. But the notion of distance never popped up. And in theory, distance doesn't matter for entanglement. And so far in practice, we have no reason to disregard this notion. But another big theory that was also prevalent is called the theory of special relativity. And in the theory of special relativity, distance does matter. It actually gives you the rise of a notion of distance. It revolutionizes how we think about space and time, right? And so I would be remiss if I didn't talk about why we reach this conclusion, right? In order for it to be a paradox, it has to break some type of convention. And this thing is breaking the speed of light is a constant convention. And by the speed of light being a constant, we reach the conclusion that it's an informational speed limit. But first, we need to talk about how we even get there, right? We have to think about why we think information can't propagate faster than the speed of light. And so let's take a trip in history. Okay, so we need to go a little back. Like we could go all the way back to the Greeks and start talking about waves from their perspective, blah, 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 blah. We don't need to do that. Let's just go back to Newton. And so Newton developed a relationship between how bodies move in the presence of mechanical forces, right? And one thing that was known at this point is that if you are moving, so let's get our favorite guy out here. Let's get Bob, right? And so Bob is on a, let's say, truck, right? So let's just draw a quick truck here. Okay, his wheels, he doesn't care about that. And Bob, so we'll have Bob driving the truck and Alice is standing in the back. Right, okay, I'm driving and Alice she has a baseball. Okay, so let's say that this truck is moving 70 miles per hour in that direction. Okay, so it's moving 70 miles per hour in that direction. And so what we would say is he's moving 70 miles per hour, right? No one would doubt that. But you have to be a little bit specific. Who is Bob and Alice moving 70 miles per hour with respect to? It's with respect to me, the observer. So it's me over here. Hello. Right? And I have no face because I'm faceless. And I say, hey, Alice and Bob, you're moving 70 miles per hour because I can measure how fast you're traveling from some point over here to some point over here. And I measure the time it took you to move between those 2 points. Like, I don't even need a radar gun. In the modern days, we would have a radar gun, right? So anyways, I'm just telling you how they knew because they didn't have radar guns back then, right? So that's how you would measure the notion of speed or velocity, right? So the guy's moving 70 miles per hour with respect to me, right? But let's pretend I don't exist right now. Just for now. Let's just pretend right now I do not exist, right? And so we're saying they're just moving 70 miles per hour, right? What I just did was took it from a modern perspective, but regardless, they're moving 70 miles per hour. And let's say Alice throws a baseball, right? And so Alice throws the baseball in the same direction the truck is moving. Well, guess what? Because the baseball is part of the truck's 70 miles per hour, all of it's moving 70 miles per hour. So when Alice throws it, and let's say she can throw it, I don't know, 30 miles per hour, right? The baseball will be moving 100 miles per hour. And then once again, we have to specify with respect to who, right? So the 100 miles per hour is respect to me, right? I'll be like, wow, that thing's moving pretty fast, right? But we don't need to do that, right? We can simply say the baseball is moving 30 miles per hour with respect to the truck system, right? Because all of them are moving in the same direction at 70 miles per hour, we can simplify and say the baseball is actually just moving 30 miles per hour, right? So when we say you have these velocities, they have to be relative to something. Are we talking about me down here? Hello? Like, are we talking about me when I'm saying hi, right? If we're talking about me, then I see the baseball moving 100 miles per hour, right? If they were tracking it, guess what they would track? They would track that the baseball is only moving 30 miles per hour, right? And so you run into these things, but this was known at this time. These are called the concepts of relative velocity. But the more important thing is that we can also go backwards, right? So remember, what if Alice threw the ball in this direction at 30 miles per hour? Well, me on the floor, I would measure it going 40 miles per hour, right? But what would they measure it? They would measure it going, I guess, technically negative 30 miles per hour, right? Because it's going in the opposite direction that they're moving into. And so you have these relative velocities, right? It really depends on who's measuring it, right? This was known at this time. Okay, so you have this concept now, right? You can measure the velocity of something and how fast it's moving. You have to be specific on who's doing it, but you can do it, right? And so you can measure all this good junk, right? And so now people started to get more interested in light, also thanks to Newton and his optical stuff. And so come around two guys. Their names are Mickelson and Morley. And Mickelson, he was an interesting guy. He really wanted to spend his life trying to get a more and more accurate measurement of how fast light was moving. And at the time, we knew two interesting things about light. We knew, for the most part, that light had to be a wave, okay? And so if you think about waves, and what everyone was thinking at this time is waves need something to travel through, right? And so just think about it. When you think about water, well, the waves use water as the medium, right? If I were to, let's see if I have something here. Like, let's say I have this wire, right? If I jiggle the wire over here, I would say this wave is traveling through the medium of the wire, right? So people really thought that waves needed a medium, right? And so what they called this medium was an ether, or an aether, because we knew, so for example, I'm going to go a little ham on the wave point again. Sound needs air to travel through, right? If there is no gas or any type of like physical thing, sound can't travel, right? Simple as that. It needs something to propagate. It needs to compress something in order to keep going, right? And so the same logic applies to light. Light, because at this time, by the way, this is where particle wave duality comes from, just so you know, is that we knew that light traveled in a straight line because it can't curve around anything, right? So we thought light couldn't curve around anything, right? Light always traveled in a straight line. Cool, right? And so, but we also knew that light was a wave because it had a wavelength, it had different properties, it could be spread apart, it could break apart, et cetera, et cetera. So we knew this. And so waves have a very interesting property, right? So if they're traveling through a medium, right, you can start talking about the wave properties. And waves can do certain things. Like when they hit each other, they can be either constructive or destructive, right? So if they're constructive, you'll add the troughs together. And if they're destructive, they'll cancel each other out, right? So depending on how the waves hit each other, they'll either add to be bigger waves or destroy themselves to almost being nothing. And you can probably see some other factors. We're not going to get into a wave course today, right? Like I said, we want to avoid the math as much as we can, but you need to understand that concept. It's called the concept of interference, right? So when waves hit each other, they will interfere with each other. So now here we're at the pinnacle of the Mickelson-Morley experiment, right? We think light travels in this medium called an ether, right? So if that is the case, then you could measure the relative velocity of light with respect to the ether. And so what these guys did, he came up with this cool device. Mickelson actually invented this device, I believe. And the device was the following, right? His device was the following. Let me get the experiment set up for us. Okay, so let's see this experiment play out. The thing in the middle is the thing that's going to split our light beam. So light moves. The thing moving up in the arrows is the ether. And you see that the object moving against the ether is slower, and you'll see a resulting interference pattern when the waves hit each other, right? And so that is what we expect to see. Eventually, it doesn't matter, for example, it doesn't really matter which direction you do this one. Like I said, they did this experiment in many different ways. They had a bunch of different issues, but you can reperform this experiment yourself, right? And so what you will see is that this is what we get. There is no ether. This is what we saw every single time. There was no interference pattern. Pretty wonky. And so okay, cool. So now we are back from the lab, right? We're back from the lab. Like I said, how do you explain that, right? The concept of an ether seems dubious at this point, right? Because we never got the expected interference patterns you would see with the relative motion of light with respect to the medium, with the ether, right? And so they devised a bunch of different ways to try to justify it, because scientists are fallible just like any one of us. They really latched on to this ether concept. They really had a hard time letting it go. So they came up with a bunch of different theories that, like, oh, okay, maybe the ether is actually doing this with respect to it. You know, maybe we have to ditch this idea, maybe we have to ditch this idea, but all of the ideas at the time had fatal flaws to them, right? They couldn't explain. So you, for example, in science, when you ditch one idea, if there were any experiments tied to this one idea, now you have to justify those experiments, right? So you might be able to explain this no interference pattern effect with the Mickelson-Morley experiment, right? But there's some other stuff that have already been explained that your model cannot predict anymore, right? So really physics was in kind of a standstill, right? A lot of people didn't pay too much mind to it. It's like, someone will figure it out eventually. The ether will live on. Waves need a medium to travel through. But then came along a guy called Albert Einstein. And Albert Einstein said the experiment makes sense if and only if you take light to propagate the same in every direction, no matter the source. And so, in a way, he was essentially saying, and what he did say is that light is constant, no matter who measures it. And so that is the key takeaway. Let's go back to our truck example, right? So what he is saying is we have a truck here, right? And actually, let's make it a spaceship for whatever reasons, right? And so Bob on the inside, he will measure the speed of light in this frame, both of us. So Bob will turn on his flashlight, right? And out goes light, blah, blah, blah. And like, it should go out in straight lines because that's what we know about light. And so Bob's like, wow, I'm so rich because I'm an experimentalist. You know, I'm so glad I learned how to do all these experimental techniques because now I'm rich, right? And then here's me living in my cardboard box, looking at his light. And I'm like, you know what? Today's the day. Today's the day. I'm gonna learn how to really use these instruments, and I'm gonna measure his light speed, and we will get the same exact speed, right? And so that's the important thing to say. It's regardless of the source, guys. It's regardless of the source, and that's really what we're saying here. Is now, regardless of the source, we will measure the speed of light to be the same. Keep that in mind, right? So it doesn't matter the exact speed, right? It doesn't matter, guys. It's that the speed of light is constant. And so what that means is, like, let's say I'm underwater, right? So, let's draw a little picture here. Right? And so now global warming has taken over. I'm even poorer. I'm struggling to swim. So now I'm like drowning underwater. And there's Bob, once again, the cool experimentalist. And instead of being a spaceship, he's so rich he can afford he can afford a submarine, right? So underwater, we know because of the refractive stuff and this or that, this light source from over here, right? It's not going to be the 299 million meters per second that we know and love, right? It's going to be some other type of speed. But the important thing is, I will measure the light coming from here to be the same as Bob would in, of course, a limited context, right? I'm not going to say like, actually, no, even, yeah, we'll just take it from there. Even doesn't matter where I measure it from. We will always measure the same velocity of light in that given area. That is the key takeaway. It's different than if Bob fired a torpedo, for example. Let's say Bob fired a torpedo, right? This torpedo, the velocity of this torpedo is dependent on who measures it. The velocity of light is not. And thus, light is constant. It has a constant velocity independent of the source. This is a first, guys. This is truly a first, right? And so how do you conclude that it's an information speed limit? Because if something can travel faster than light, then it's no longer a constant. Then I can start talking about light in a relative velocity context. But we have yet to see a scenario where that occurs. And thus, the information speed limit is born, right? If light is a constant, then that means nothing moves relative to it, right? Sorry, light does not move relative to anything else, right? Everything moves relative to the speed of light in your given medium. That's all it is. That's all there is to it, right? And so with that one thing, we ditch the ether concept. We don't even hear about it anymore outside of like some fringe theories, right? And light is a constant. It's a universal speed limit, right? Because of the fact that it does not move relative to anything. So with that being said, we have now finished why it's a paradox if quantum entanglement can travel faster than light. If it can spread information faster than light, then now we can start talking about information relative to light. And so now light can be relative to something else. It can move speed of light minus 20 in one direction, speed of light plus 20 in another direction relative to entanglement. And so we will see how to resolve this paradox in the quantum entanglement thing when I get a little bit better at animations. Thank you for paying attention and watching this episode.